Hello, hello, hello. Welcome, everyone, to our next episode of the Julia Dispatch. I'm Chris Rakakis.
And I'm Michael Thiemann. And today we have with us the man himself.
The big man himself. Yeah, Jeff Bezanson. How's it going?
Hi guys. Yeah, thanks for having me on. I don't think I'm the man himself.
Well, how would you introduce yourself? I mean, you got a lot to introduce, so how would you introduce yourself?
Well, I mean, I'm known for being one of the co-creators of Julia. That's basically what I'm known for.
And co-founder of JuliaHub.
Yes, of course.
So something that I've recently learned actually is that Julia was around, or the project, like the GitHub repo started before you started your PhD. And so from someone who has only recently come more into Julia, I associate your PhD thesis mostly with the creation of Julia. But like, can you give me sort of a background as to like what the origin story was before that started?
Oh yeah, sure. There was actually 1 year where I was a research assistant at MIT. So that's how it actually started. Alan took me on as an RA. So I was working there as just a in that capacity before I was a grad student. I think at that point we were sort of still deciding what the best way to kind of structure and do the project was, and that was a way he could bring me on to start it quickly. And then he sort of thought about, how should it proceed? Should it be a thesis? Should it be a different kind of research program? And he ended up deciding that the easiest way to do it would be for me to apply to grad school. So that's what I did. And I was kind of trying to avoid it because, the application process and everything. If you can skip it, you might prefer to skip it. But
who wants to do a PhD?
Yeah. But it's like, okay, it's gonna make sense for me to do this as a PhD. So then after a year, we switched to that.
Okay, that's interesting. So you actually wanted to avoid the whole academic setting initially.
Well, it was in an academic setting anyway. It was still a research group at MIT. But yeah, I mean, I would have been willing to do it. Not necessarily getting a degree. I mean, that would have been okay. It's kind of nice to have the degree. That was good in some ways too. So, but it wasn't my number one goal. My number one goal was to do Julia, and if I can do it as a PhD, okay. But another way also could have been okay.
Okay, but did you had a vision like how Julia would have looked as a project if there would have been no academic background to it, like a pure project?
I think it would have been very similar. I mean, it was an academic environment anyway. It had to be done that way. That was definitely the best way to get a project like that started, for sure. So I don't think it would have been that different.
Okay. Though, what really brought you to be working on this? Because Julia is more than just a programming language, right? It's like a programming language which is trying to solve this problem of we want to make sure that we can do fast programs for engineers and scientists, right? So what's the thing that brings you to like this problem statement of, oh, I wanted to build something fast for engineers and scientists? Like, what brought you to that question? And also, what brought you to Alan? Because Alan had a background of Alan Edelman was in the math department for random matrix theory, right? And so what was this whole trajectory here to kind of bring you two together to then say, you know what, we're going to solve programming languages for engineers now, right?
It's a really winding path. It's really bizarre, actually. I mean, I think if I could guess, probably the original origin point of it was when I was in college, and I believe it was in the first. There was a semester where I learned both Common Lisp and MATLAB for the first time at the same time in different courses, and somehow that sort of that caused some kind of a epiphany. I was looking a lot into Lisp, and at that time on the workstations at Harvard, Allegro Common Lisp was available. And so I was really, really impressed with that system. It's a really good implementation, and I benchmarked some things, and it also had a disassemble command where you could write Lisp functions and disassemble them, and it would show you the assembly that it compiled to. And it was pretty amazing. This blew my mind. that it could do this. And then I looked at how people were doing technical computing in Python or MATLAB, and it was so much slower, and it didn't seem to have any of this kind of programming language technology. And I just thought, this is incredible. This stuff is available here, and nobody is using it. It just seemed like a kind of market failure to me that had to be corrected in some way. And I didn't really do anything about it for a very long time, but it's sort of like an obsession that stuck. And I, played around with programming language kinds of things on the side, sort of always wondering what to do about this. And until eventually I found that at Alan's last startup, Interactive Supercomputing. And then even though it was years later, I sort of had this aha moment where I was like, oh, maybe these guys are going to fix this problem. I should go work there. And then, of course, Julia later came out of that, because that's where I met Viral and Alan.
Yeah. So I mean, so how do you make that concrete step, right? Because there's this general phenomena, especially on the internet, of people who know the Lisp aficionado that's just like, oh, Lisp did it better back in 1970, right? Like that's a whole thing, right? But how did you go from that, oh, I learned Lisp, and Lisp had a lot of really cool things, and now we have these technical computing languages, and you know what? Let me take a lot of these ideas that I learned here and build a better technical computing language. Like, what was that step where you actually sat down and you're like, you know what, it's time to start building the language now?
I mean, that happened as the interactive supercomputing company was being acquired and drawing to a close, and I guess my mind was kind of starting to wander, and thinking about what to do next. And I just somehow a bunch of threads came together, and these ideas sort of coalesced. And we had actually at that company, we worked on a system where there was actually a little multiple dispatch system implemented inside it, which that brought in another little kernel of an idea, and I started to just sort of get this vision. I think I see a possibility of a new language, and for some reason I ended up talking to Viral about it, and he said, you say the same things that this guy Stefan I know says. You guys should talk. And then I talked to him, and it turned out, yes, we were thinking the same thing. And there you go. But I don't really, I don't really know how did this exactly form? Somehow it formed.
Okay, but you already mentioned multiple dispatch. Like, I mean, these days, to me, it seems like this is one of the big cornerstones of Julia that is absolutely defining it and a distinguishing feature with respect to other languages. Like, was this something that was already clear to you, that this is going to be like the big feature that you absolutely want to have, or was there a period where Julia could have ended up without multiple dispatch?
Yeah, there was actually. It was really not that clear for a while. Mm-hmm. The main reason we first started saying, well, maybe we should do a multiple dispatch language, there's basically just two reasons, I think, which was one, because you've got mathematical operators that all take two arguments, and doing the kind of double dispatch stuff like that Python does is not very satisfying with the multiple methods, the add and the radd. That's not very nice. And so if everything has two arguments, you've got to be able to dispatch on both of them, because we wanted this to be good at math. So that's kind of one reason, which is really, that's it's kind of a reason, but it's not enough of a reason to sort of build the entire system on multiple dispatch on every argument with all of this stuff. It doesn't necessarily motivate all of that, right? But so that, and then the other reason,
it'd be easier to implement plus, so therefore multiple dispatch, right? That'd be
right. It doesn't 100% lead you to that necessarily, right? So, and the other reason was just that we thought it was cool, and it would be kind of a differentiator, because I envisioned, if we made this whole other language and it just sort of had the same object system as Python, say, or similar one, it's kind of, well, what's the point? Why would I switch? It's sort of, I felt it needed to have a big differentiator. It needed to be distinctly different. It would make the effort more valuable. So that was kind of the other reason. But then once we decided, okay, we should probably do maybe some multiple dispatch, we also thought for a while that maybe we'll also need another single dispatch object system as well, because maybe you don't want to use multiple dispatch all the time. So that was a possibility for a while. And then but we just kept writing everything with the multiple dispatch thing we had, and we said, you know what, no more features. This seems to be sufficient. So why add features? And then what we didn't really know was just how successful it would be, and how much stuff people would do with it, which went far beyond what we've envisioned at first.
So I mean, there's this famous talk from Stefan about like the unreasonable effectiveness of multiple dispatch, but like, was this something where the both two of you were surprised as to how this would take off? Or like, you also mentioned the Python specific write dispatch. I'm not completely sure about the technical details in Python here, but I think our add is also single dispatch, right? Like, was there ever a time where maybe there would have been like a two dispatch, like a single dispatch, two dispatch, and then, but not three or more dispatch things?
I don't think we considered that. I mean, it seems silly to make, n equals 2 a special case, so I don't think we would have done that. But I also think, multiple dispatch gets a lot of billing, but I think it's really, in some ways, it's not really the best way to describe the language. There are lots of other ways to look at it, and ideas that are kind of almost bigger. So like one thing, although it's not as commonly used term, so people don't tend to use it, but you should also really call it external dispatch. Because the methods are defined outside of the data types rather than sort of inside of them, the way they are. Because you can also have, internal multiple dispatch, like where you have typical classes with methods, but they also dispatch on other arguments. That's a possible design. And so, but the external dispatch is really, to me, as important as the multiple dispatch, because it lets anyone add any method at any time, and all methods are kind of on equal footing.
So it to me as sorry.
Yeah, which is what gives a lot of the flexibility. But yeah, go ahead.
Yeah. So to me, as someone who really always had a soft spot for the functional programming languages as compared to the object-oriented programming languages, Julia really felt like a very funky form of functional programming language, where the primary way of thinking about functions and data types as opposed to objects that come bundled with methods was neat. But then the multiple dispatch throws this weird extra twist on it. It's I love it.
Yeah, no, that's what I really like about it, is that everything is just a function in the same way. It's not like, oh, this is a method. Here's a bound method object. Here's there isn't any different kind of function. There's just one kind of function, which I think is very nice.
Yeah.
So I mean, and you mentioned that one of your inspirations there was Lisp, right? And you can see a lot of the Lisp inspiration inside of the programming language with the macros and everything, right? Are there any pieces of Lisp that you wish you kind of carried it along more, or do you feel like this is the right amount of Lisp in a modern day programming language?
I think this is a pretty decent amount of Lisp. I think it's the right amount. Of course, there are those who want S expression syntax.
Yeah.
I actually do. I do slightly wish we had a good alternative S expression syntax front end that you could use to ideally write both the source level language and the IR. If there was a nice standard S expression syntax for that, which we could have if we wanted. And I think that would actually be nice. Most people might not use it, but it should be kind of available, I think.
You're not missing the parentheses from the original Lisp syntax?
Yeah, well, I think it should be available. Yeah, I think that it should be an alternative. A lot of people would probably say no to this because they think there shouldn't be, two syntaxes, just have the one syntax. And yeah, I'm sympathetic to that, but I do think it would be fun to have that alternative available.
It just if just only to live up to the XKCD comic of here, we are handing over the parentheses from the grandfathers.
Yes.
So, one more bit, like to get to know you for the listeners who might have not yet had the pleasure of meeting you in person or just hearing from you for the very first time, although I hardly can imagine that anyone listening to a Julia podcast would not have heard you before. So seeing that you are in this very center of the Julia universe, I'm guessing whenever you go somewhere and you meet people in a Julia context, they always want to talk to you about Julia, right? But sometimes people need breaks. Like, what would you wish that people would talk to you about if not Julia?
Well, it's perfectly fine to talk to me about Julia. I mean, there's nothing wrong with that. But I mean, I also I like to cook. I really like to cook a lot.
Okay.
I do several times a week. Typically, I typically cook several times a week. Actually, I really like that. It's my way to relax in the evening. And I play violin. Classical violin is my other big thing. I'm in a community orchestra.
Oh, you might have a JuliaCon orchestra someday, right?
Yeah. We almost, with David Sanders is a very good violinist, and we almost, we could almost try to put together a JuliaCon quartet or something.
Ooh.
If enough people ask for it by watching this podcast, if we get enough upvotes on that, maybe we'll do the JuliaCon orchestra.
Yeah, let me know if you want to do the JuliaCon chamber orchestra or even a quartet. It's fine.
Will you allow guitar to play as part of your orchestra? Because I only do electric guitar and I also do drums, and so I don't know if that's the right vibe.
If you can find a piece, or if you can write the piece for electric guitar and string quartet, then it can happen.
All right, you heard it here first.
Someone do an arrangement.
So this is the call to action to the listeners at home. And yeah,
I bet you could do a really good arrangement of some songs for electric guitar and string quartet. I bet that could be good.
Oh, for sure.
All right, let's get down to the meat. So recently, you've been mostly focusing on compiling Julia to binary formats. That's both the talk that you presented at JuliaCon Local in Eindhoven in December last year, and also, of course, the talk you presented at JuliaCon this year. So, tell us about that.
Yeah, and this, I was thinking about this, and this has some interesting connections to the kind of design basis of the language, because some of the things we were thinking back then was, let's look where is the world going? What can we exploit in a programming language as far as how the computing world is changing? And I saw, software is running on server side, right? Well, you've got server side software is almost everything, or people are maybe working interactively in a notebook, say. Or you're sending someone source code based someone who you're collaborating with, or open source, you're sending source files by Git or something, right? So this is how sort of I saw, at least in my world, everything's kind of working. And in no case there do you pass a binary around. You never hand someone a binary on a floppy disk anymore. But that used to be how everything worked. And so that to me deprioritized the compilation model of that say C has, right? So in the C Unix world, where that stuff was invented, low compile times and small binaries were absolute top priority. I mean, people were always running out of disk space. They were very, very short on storage and memory, and so all of that footprint had to be as small as possible. And that was almost the first priority. I mean, it was that high priority, And so we said, well, we don't really need that. I mean, it's nice, sure, small binaries are nice, but we don't really need that. How can we, what can we do if that's not a requirement anymore? And you can do very aggressive specialization of everything. We will recompile libraries just anytime we feel like it to optimize it for what you're doing with it. And it's kind of profligate, but I think it's the right thing to do because we have the resources, we have the memory, we have the CPU cycles for it. So do it. You can get a very high level, very flexible programming model and great performance by just specializing everything on everything. And it's fabulous. And the only cost is, like a little bit of compilation time, and a lot of code gets generated because there are lots of combinations. But that's That's okay. You know, a gigabyte's not even that much anymore, right? So we ended up in this space where we do basically more like a whole program compilation model as opposed to the C style separate compilation. So that's sort of where we have been. But now we've gotten to the point where, okay, that was deprioritized. But now as we go down the list of what stuff haven't we done yet, we've now basically just hit this item on the priority list. It wasn't the first priority, but it was like the sixth priority or something. So now we're at that item, and so and people are starting to feel the pain from that, and they're starting to complain because some people, in fact, do still need to deploy binaries, not on floppy disks usually, but they need to deploy binary anyway for a variety of reasons. And so it's like, hey, you got to have this feature. So we've hit that point, and so we're getting there now.
Okay, so the reason that this is starting now is just, okay, at some point this needs to get done, might as well, or well, not might as well do it now, but now it's time to have the priority. Okay.
Yeah, I mean, we spend a lot of time thinking about priorities. We're sort of like, what's the worst problem right now? Is it this or is it this? But for a while it was the time to first plot, right? That's another very famous problem. That would be, and so let's see, is it the time to first plot or the small binaries? Which one is worse? Time to first plot. Okay, so we did that first. And that's basically fixed now, I'm happy to say. Yeah. So now we're sort of, okay, all right, people are complaining about the small binaries. That's the worst thing now. So, we're just always discussing this, either on the triage calls or just amongst ourselves. It's what feels like the biggest problem.
Yeah, but I mean, I want to kind of go back to something you mentioned about 2-3 minutes ago. You mentioned some hate towards people still using floppy disks. It sounds like we're not going to put tier 1 support for binaries for floppy disks. Did I get you on record for that?
No. I'm completely on board with floppy disks. I'm just saying that that's unlikely to be a main use case these days. But I'm perfectly happy to support floppy disks.
Yeah, so everyone out there still deploying with floppy disks, it will be supported. I mean, well, one of the things you learn with open source, right, is that, we might make fun of those kinds of things, but then, the person who has, Windows 32-bit XP will come out of the woods and say, hey, your newest beta version no longer builds on 32-bit XP. What happened, right?
Yeah. Well, and Julia Hello World now does fit on a floppy disk, so we are compliant.
There you go. Nice. So how do you know that it does fit on there though? Like, because there's always a story behind it, right? So how do you know who tested that?
Okay, well, that's a good point. I could try to actually copy the file onto a floppy disk. I have not. I admit I haven't actually done that.
Okay.
Right. And so if I understand correctly from the presentations, you're now at the point where you can both create like standalone executables where I can just say, okay, run this executable and then it does exactly what I programmed it to do. But you also at the point where you will be able to have shared libraries that you can link to other shared library systems.
Yeah, I mean, those features basically come online at the same time because a shared library and an executable are basically the same thing. It's just that the shared library doesn't have a function called main, but other than that, they're basically the same thing. So it's basically the same. And they're technically not yet, or at least not by default, standalone. They do link against the Julia runtime, but it is possible to statically link everything together into one big self-contained thing. But I think people don't usually want to do that because you can at least share the runtime.
No. So what were the biggest changes to the language that were required to kind of make this work out well? Like I assume that it didn't just happen, right? You had to kind of change something about the compilation model. So at a high level, can you kind of give an idea of what in the compilation model really started to make small binaries a possibility?
Yeah, it's sort of interesting because this is the kind of thing that it changes both nothing and everything. I mean, it changes nothing in the sense that there's no like language feature that's out the window. Like it's not like, oh, there's no garbage collection. Nope, GC is still in there, of course. Or it's not like, oh, there's no I don't know, multi-dimensional array concatenation. I don't know. It's not like there's some feature that's like, oh, that's that's gone or that's changed or some syntax has to change. No, like nothing has to change. It's the same language. You're just compiling it in a different way. So in that sense, kind of nothing changes. But in another sense, sort of everything changes because you have to be able to, you now suddenly have like these restrictions that have to be placed on your program to be able to meaningfully cut it down, because we have to be able to prove that a large amount of it is not going to be called, which is doable. It's fairly tractable in Julia, because we're kind of close to a statically typed language. Like, it's a high percentage of Julia code that actually is statically typable in general. So that sort of makes this pretty tractable. But it means that certain things won't work if you do certain kinds of runtime execution or runtime code generation. Certainly doesn't work. Certain kinds of reflection won't work as expected, because we're going to delete the thing that you might be, trying to reflect on.
Well, let's take a step back there on that, right? So, because you're kind of starting to get to, what is Julia C and Julia C's -- trim option, right? What are they doing, and why does this matter for these small binaries?
Oh, yeah. So the way we get the small binary is with this. Yeah, we have this new option to this new compiler driver script, and you put -- trim, and then it will try to remove everything that it can prove is not going to be reached from your entry points, like main.
So you say, oh, I have this function and this, and you bring in this whole package, like, differential equations, which has like 500 solvers, right? But then you see, oh, my main function is just calling this one algorithm. So delete 499 functions out of here, right?
Exactly.
And so, are there any difficulties on trying to find out what you can and can't trim? Because, at a high level, it's just like, oh, that means that you can delete everything, right? But you still have a dynamic language and everything. So what are the limitations of how much you can truly trim down? Can you make it as small as you only get that one? Or what does the programmer need to know in order to use the trimming effectively?
Yeah, so it's funny, because in theory there's sort of a knob you can turn, which is that we basically start walking the call graph of the program from main to try to find everything that might be called. But then you have to just sort of make a kind of a judgment call about how much of the graph you're willing to explore, because we could do the what I would call like the trimming. The troll version of it is, if we come to a call site where we don't know what it might call, we're just like, well, this might call everything, so we'll include everything. And then your trimmed binary is exactly as big as it was before. We're like, here, look, I trimmed it. Well, which is so you want to avoid that, because that's going to put the programmer in an awkward position where they expected a smaller binary, they didn't get a smaller binary. So it's like, okay, well, what do I do? How do I get this? I want the small one. How do I get that? And so I think that would be a poor user experience. So we have to kind of decide when the call graph is getting too bushy and there's too much fan out, and so we instead will give you an error. So you can say, okay, this call site is too dynamic. We don't know what this calls, so you have to narrow it down somewhat.
And what's kind of like the idea? I know that the heuristics will definitely change over time, but like, what's the high level on the heuristics for, so let's say I have an abstract type, like, this function can be called on number, and you don't know what type goes in there, right? There's like 10 numbers. Will you say, oh, I'm going to create a version of this function for all 10 numbers and stick it inside your binary? Or, if I go to 100 numbers, or is it going to say, oh, that's too big? Like, is that how the heuristic is working? Or is it like whether it's bounded or unbounded? Kind of give a sense of what your thought process is in there of what to keep and what not to keep.
Yeah, so what we encountered that was kind of the most useful thing that we kept hitting that code in the real world needed was basically, if you could think of it as like if you tried to map a simple single dispatch style object hierarchy kind of a thing, where you have a virtual method, and then you have various implementations of it for various classes that you have, and each one of them is just the method for that class. And so it's just a kind of simple dispatch over, n existing concrete types. And that was the case that sort of we needed to support and that we hit immediately, that seemed like we could handle. And so basically, if you have a call site where we might not know the arguments types, but if all of the possible matches for that are just a bunch of declarations or just a bunch of definitions of that method, each for just its own set of concrete types, then we say, okay, that's not unreasonable. We can just, dispatch to whichever type of that you might happen to have. Of course, there's a risk that maybe you're not using one of those types at runtime, in which case that'll be more than more than strictly necessary. But we might be able to narrow that down some way in the future.
So you'd say something,
but that's working pretty well for now.
so trying to like pull this up to a high level, if I'm thinking like, okay, you have like, floating point power and you're like, okay, we don't know what you're going to do power against, but if it's float 32, we know how to do it. If it's float 64, we know how to do it. If it's complex float, and there's like this finite list, and every single one of them is a concrete, like, a very specific piece of code for all the different cases. There's n cases we can do. So therefore the binary is just going to stick all n cases in there. But if it's kind of this unbounded, like, anything can happen, like you need to specialize based off of every possible new number. No, we're not that's too hard. Is that the kind of thinking there, or is it a bit more?
It's about limiting the sort of fan out and exponential blow up of methods, because if you're going to allow like fan out from one call site, for that to be okay, because that could lead to more fan out from each of those things that you visited, and then it could start blowing up. But if each of the things from the first fan out is concrete, then those are going to tend to be those methods are going to tend to have very, very static call graphs where we can fully resolve all the dispatch, and so there isn't going to be any more fan out. And so that generally seems to be the case. So it keeps things kind of manageable. But this will evolve. It might be it's going to evolve in various ways probably.
So it's still kind of dynamic, but you're finding, is it static enough for me to build a small binary effectively, right?
Yeah, it's like how static does the call graph need to be? Which is you can demand that every call site have one target, or there's various different rules you can have. There's all kinds of ways you can restrictions you can put on what does that call graph need to look like for this to work.
Hold on a second though. So I think I heard the keyword single dispatch earlier, and the picture that I currently have in mind is like, okay, so the exponential blow up of the dispatch happens because you essentially create the Cartesian products of all the possible types. And the way I understood what you just said is you're only looking at, like, you're even disregarding the pairwise combinations, but you're only like, if you hit a call site where there is no pairwise differences in the calls, then you're going to support the n types, but you're not going to consider the, let's say, float 16 with float 32 combination and vice versa. Like, did I?
Oh no, we will. Yeah, we will. There's no like restricting to only looking at one argument or anything like that. We don't do that. So
but it's like you can still have any, right?
Yeah, you can still have any combination of types of things. You can still use any combination. In fact, you might use quite a good many combinations of types, and then we'll happily compile them all. As long as as we compile all of those, there isn't too much fan out from method to more methods to more methods.
Okay.
And I guess the fan out, that's more on like the output type, right? So I guess, you might not know what goes into equals equals, but if equals equals is always giving you Booleans on your output, then you're like, okay, then at least there's not too much stuff, because everything that comes out of here is Boolean. So everything beyond this can assume Boolean. So there's still not too many methods. Is that kind of the thinking there, or?
Yeah, I mean, and that's sort of a general feature, and it's of the way we do type inference in Julia, is that you can kind of like do this kind of type recovery where you might not know what's happening for a little while. There's like a few calls that are kind of dodgy. But at the end of the day, this is just Boolean. So okay, we're okay again. So and with that, that happens a lot, and it's very very useful that we can do that. You don't want to have, and in fact that's another sort of key language design things. You don't want to have, if you have one call site where you don't really know what's going on, you don't want that to completely ruin your ability to infer anything about what happens after that. And so we have that property, which is very, very useful.
One of the things that kind of, should be coming up with this is, now that we have this new feature, normally major headlining features like this also tell you something about, how you should be programming, or, what kinds of programs are good for this or bad for this. So, do you have any example? I mean, you don't need to really just call someone out there and be like, oh, hey, I was looking at csv.jl and that's the worst program for this, right? So you don't need to do a call out, though, if you want to, it's kind of fun, right? But, do you have examples of like, codes that will probably need to change in order to really make a good use out of the static compilation, or do most codes already kind of get like a 50% benefit, and with a little bit of effort they get a 90% benefit? Like what's the how is it looking on the real world codes that are out there?
So it's a little bit all over the place, and it's so the first thing is that it depends on the application. It depends on the end executable or shared library that you want to build and what it uses, because you could have, of course, a package that does all kinds of dynamic stuff and is hard to compile statically. But if I only use one simple function in it, then it's going to be fine, right? So it's kind of all over the place. But the obvious ones that are going to be difficult is probably things like data frames. That as part of its design uses vector of any, where you can have these heterogeneous vectors of vectors, and so that's going to be difficult. Of course, that's probably not going to work very well. But the thing that people really want, unfortunately, they can't have, which is what everyone really wants, is to our great Julia package developers always want to be on top of everything, and they're like, okay, I want to CI this. How do I want a badge? I want a CI badge that says this package works with trimming. They want to test that.
Oh, I want the small binary badge for sure.
Yeah, exactly, right. So that's kind of what everybody wants, and unfortunately, you can't really do that because it depends entirely on how the package is used. That's sort of it's sort of part and parcel of this compilation model. So you can't once and for all just say, this package you can do trimming with. It's kind of not really workable.
But there is some tooling that you had also been working on recently, right? That kind of helps programmers towards this area. So can you describe a little bit about some of these projects that are kind of going towards more static analysis, things like aleccheck.jl, jet.jl, and how this is kind of interacting with this, static binary building kind of world?
So we have static analysis is a big growing area in Julia, and I think actually this, after the small binary stuff is sorted, that might actually be the next big priority item, is to focus a lot more on the static analysis tools. But we already have some. Yeah, we have the aleccheck, as you said, that will statically ensure you're not allocating memory for cases when you don't want to be dynamically allocating memory. And there's jet, which can find a variety of issues that basically exposes and exploits the data flow analysis results we have inside the compiler to tell you stuff about that. And it also now has a mode that can basically predict, if you will, if trimming will succeed. Although you can actually just try to do the trimming and see if it succeeds or not. Of course, you can just do that because that itself has the error checks for that built in. But I think I don't want to be too pessimistic about this. I think for some packages it might make sense to add some kind of CI for that. Like if you have if you're developing a package that amounts to like libm, say, maybe every function is just a function of float 64 or float 32, and so and it could be, say, called as a clibm kind of a library. That thing you might as well just you could check that's compatible with trimming, because all the entry points are sort of fixed. And then there are libraries that are more generic, like more like template libraries, if you will. And with that, it's not, you can't really do it in general, but you can do it in some cases. So people might still, be able to do that sometimes.
So I got nerd sniped there for a second, because when you said you will not be able to have the small binary badge because it's essentially not fixed how people will use a package. Like I was thinking for a second about an a la carte compiled library, right? So naturally I often tend to think about the differential equation package, and then so if I want to create a shared library just out of differential equation package that I will not touch after I shipped it, but then I could sort of say, okay, I want to compile one version that is just assume float 16 everywhere. I want to compile one version that is float 32 everywhere. I want to compile one version of it where I disabled all the stiff solvers. I want one version where I disabled all the non-stiff solvers. Like I'm now I'm already thinking in this sort of, okay, I want to create a shared library, but I want to sort of have like a maybe even a GUI of say, okay, I want to have this and this and this and this, and then all the rest I'm going to hide from for shipping out. Like, does this make any sense to you? Like,
Yes,
am I going
yes,
nuts here?
no, that's a great idea. In fact, I mean, that's exactly the kind of thing that you can do. So like if you write, say, BLAS in Julia, you'd have, the Julia version would support, say, any Julia data type. So, it would work with absolutely everything. But there's also a flavor of that library that you can ship as a C library, callable from C, which just exposes the typical BLAS interface of just single, double, real complex, and so you can just say, okay, just take that sample of the possible implementations from this library, and build a binary of that, just those flavors of all of the functions, and then you could build that binary as part of your CI, and you could check that keeps working. Yeah, so that would be a great thing to do. Yes.
And how does this? I mean, the version 1.9 headlining feature was we can now make binaries of packages, right? And now we're saying, okay, now we have binaries of these applications, but they're not quite the same. So could you give like a comparison? What is similar? What is contrasting between package binaries and these binaries that we're now building for applications? How are they different? How are they similar?
Yeah, that's a very good question. So, I mean, they're similar in that they are both files that have machine code in them, I guess, but they're quite different in that the package images are basically designed to be incremental. So they get loaded into and basically merged into another running system. So they have a lot of extra information in them that allows them to be correctly integrated into running Julia runtime, where all that other information has to be available to make that possible. And also that all the compilation that tends to get done for package images is basically speculative. It's let's precompile a bunch of stuff that we think you'll probably need. Whereas in the trim binary, you only want to compile things that you definitely need because they're definitely reachable from your entry point. So in the trimmed world, the binary is not going to have any of the metadata because it's kind of large. That tells you things like like the call graph for information that says, like, if I add this method, what functions might that interfere with to do this so-called invalidations of invalidating compilations that need to change when you add a new method. So we drop that capability in the trimmed binary to make it as small as possible. So those are basically a totally each one of those is just going to be a closed world where you can't add in new code anymore.
So, I mean, and now that you've done all this, right? You start to get these small binaries. The cases that don't tend to work as well. What is something that you're like, what? I would actually want to change this in the language if I want to make small binaries much easier, right? There's got to be something that's come up of like, oh, this is the one thing that kind of is the biggest issue with small binaries. So, is there anything that you kind of found as just like, oh man, if I really wanted small binaries to be better, here's a change I would suggest like immediately.
Yeah. Oh, absolutely. Absolutely. I mean, the first thing you try, of course, when you do this feature is Hello World, right? Let's get Hello World working. And if you do Hello World, guess what? It doesn't work because we have the default. If you just print a string, the default output stream is drawn from a global variable, that's stdout variable in base, which is totally dynamic because you can change it. You can redirect it to any type of IO or almost any type of IO object at any point. So we don't know the type of, at least in the way we're doing things now, we don't know the type of the standard out stream. So
Oh God.
Hello World itself is a problem. So that's something we're going to have to work on. So there is an alternative because you can print to, there is a stable core.stdout stream that you can use instead. That's the workaround for now. So if you just use that, it works. But that's something we're going to have to address one way or another. There's various ways we can address that, but yeah, that one has been a little bit of a thorn. The other thing that's been a little bit of a thorn is the init methods, because the thing about the init methods in packages is that if you have one of those, we promise to run it on startup, right? So in this case, every one of those becomes an entry point that we have to include. Because the init method might do anything. It can who knows what it's going to do. It can set up various variables. It can call,ccall into native libraries to set up some state that you can't see, so they might do anything. And all we know is we're required to run them. And there's no way to know, whether you're depending on those having run or not. So we have no choice but to run them. So we have to include all of those init methods and everything they call, even though, you might not really need any of that stuff, because there's no way we can really work that out. So I would, if I could go back, maybe I would never add init methods in the first place to the language. I'm not sure how we would solve all those problems in every case, but I think there are other ways you can do it. But those have been a thorn as well, for sure.
Yeah, they do tend to get abused.
Have there also been situations where, like you mentioned earlier, that you have to just make these decisions of judgment calls? Okay, I'm going to include this, I'm not going to include that. Like, have there been any decisions that were like really you were split either way, and it was an internal struggle? Or are you fearing that there will be more of these decisions coming as you progress the work on the compiler?
I don't know. I mean, it's we just have to fight through this stuff. Anything like the standard out thing in the base library that's not working out, we just have to come up with some hack to get around it, basically. So we'll just get through it.
No sleepless nights on, I wanted this, but I don't want this, and I just cannot decide.
I mean, we might get to that point with this. We were just eyes on the prize. We just did whatever it took to make this possible. And, you got to get it working first, and then we're going to worry later. So maybe I'm not at the worrying stage yet.
Staying true to we want it all, and we will get it. Yeah, nice.
I mean, it hasn't merged yet, right? So, like, isn't this the worry stage right now? All the tests trying to get them to pass.
The tests do pass, actually.
Okay.
Yeah, I think it's pretty much mergeable. Actually, I'm not aware of any major roadblocks right now. Actually, I think it just last week it basically got into a mergeable state. It's test pass. There's CI for it. It's documented.
By the way, I'm guessing it is online available, but I have not seen a link in the JuliaCon talk or slides. Like, if I want to play with this right now after the recording, like where should I go to?
Oh yeah, you have to use a branch from a pull request for it, which
means wait for a little bit.
I can quickly look up which branch that is. Let's see here.
Well, I think for most viewers, I think that's going to be when version 1.12 comes out, or the early beta versions of that and such.
Yes, it will. Yeah, so when 1.12 releases start coming out, it will be in there. But it's if you search the pull requests for add trim option, that's what it is, or it's also number 55047.
All right, I will
pull request.
Okay, I will put it in the show notes because I considered this a service-oriented podcast and people want to get their hands on it.
Yeah, so build that branch, and then in that pull request, there's just quick instructions of how to try it out.
All right, nice.
Yeah, and then open issues on the Julia Lang repo, because this is how things improve, right?
Yeah. Oh, we just hit pull request 55555, and it was reverting something. I was so disappointed.
Oh, what happened to
Michael?
camera?
I think that something's happened with your camera. But yeah, so I mean, well, but I guess one of the things to kind of bring up, right, is that reverting code. Isn't that kind of your claim to fame? I think you mentioned before that you have a lot more code deleted out of the Julia repository than you have code added. How did that come to be? Like,
I think that's Viral who that's true of.
Okay.
I believe that's Viral. I think. Let me see if that's still true. But I know that was an infamous story. That was an infamous event that happened in our repository history, where I think Viral just YOLO'd some virtuosic shell script that he whipped up, which somehow, I think in one step, like downloaded and pulled in a bunch of source files from something and then just committed it right onto master, like sort of all at once. in one flourish. And I think all of them, all of the downloads like failed or something. So all of them were just like error pages. And so there was just this massive amount of trash that just got dumped into the repo, which he then had to delete. And there's something else like that where he had this like massive amount of deletion.
Okay, well, the
Let's
early
see,
days.
Does it say that? How do you get the total additions and deletions? It doesn't say actually. I think it used to give that number.
Oh, yeah, it used to give that number, but I guess it doesn't in the new contributor stats that they just put together.
Yeah, this is something. Maybe if you click through. No, yeah, it used to have plus and minus lines. It doesn't seem to have that now.
Oh, that's sad.
Oh, that's disappointing. Okay, so maybe somebody knows how to get that. I don't know how to get that.
Wondering when will this be like 1.0 and then the next item on the priority list? And what is the next item on the priority list after the compiler is completed?
Yeah, so this is going to be kind of experimental for a little while, I guess maybe for a release, and then maybe we'll declare it stable a release or two later. But I think the next thing I would like to do is actually have a proper separate compilation model, which is, so yeah, this is just smaller binaries, but it's really just about the size at the end of the day. It doesn't really give you separate compilation the way C has. So that's something I would like to add, which is basically, it's a little bit more of a language feature, which allows you to have multiple of these kind of closed, sealed modules of code that we will not reanalyze or recompile again, and they will have fixed behavior, and then you can call them externally. And so there's kind of that's just through interfaces. So that's sort of a feature we don't have. We have the only thing we can do now is basically all the code you load and all the methods goes in one big pile. And you can't you're using one version of the global method table at any given time, and you can't have sort of alternate things communicating with each other. But that's something I'd like to have.
So something
and I
like
think a lot of the voices.
Sorry, something like object files in when I compile C code, or
yes.
And I think that a lot of voices who've really been asking for binaries, one of the other things that they've been asking for is cross compilation. So where's cross compilation on this roadmap as well? Can Julia in theory do cross compilation, and how far away does it look like it is?
Yeah, so we can do it in theory, and that's also very much in the roadmap on the building binaries type of stuff roadmap. It's definitely in there, but there's some challenges there, of course. So one thing we do a lot in Julia is, in the Lisp tradition, you can run any code anytime. The whole language is always available. So
always back to Lisp.
Yeah. So you're when you're loading a package, which means like when we're basically parsing the code effectively parse time, you can run code, which people use to do things like programmatically define methods, for example. It's pretty popular, but you can do anything in that code. You can potentially inspect the platform that you're running on and do things based on that. And so when you do that, you're basically assuming that the host and the target platform are the same. So any of those kinds of assumptions would not hold anymore. So we would have to have some way that you'd have to manually query the target to decide what to do instead of just talking to the host platform. So that's the kind of thing we would have to think about. But other than that, it can be done. In some ways, it's sort of easy because we can, when we're generating code, we could just sort of set LVM to a different backend and then just let it go, and then now you have your code for a different platform. So that's sort of in some sense it's easy, but I wouldn't expect that to just immediately work without any other sort of effort. And there are also a lot of good options for doing this sort of thing, like running emulators, for example. Like you can run, or you can for example run a 32-bit tool chain on a 64-bit system, and so you can just essentially run the target platform on your host and just compile inside that. And for some cases that will work, and then in that case we can already do that because you can always do that. So for some cases, not all, but yeah, that's going to be in the roadmap somewhere.
Yeah, somewhere. You want to put a date on it?
No.
That's the scariest thing. Next year, right?
And the other thing is we're going to have to kind of do that on an on-demand basis. It's a little bit hard to say, yes, we now have cross compilation, because there are lots and lots of possible targets. They all have different issues that will come up. So it's really kind of a one target at a time kind of a situation.
Mm-hmm, mm-hmm.
Or handfuls of targets at a time, maybe.
So as someone like I love the theory behind compilers and just like general science. And one aspect of the compiler to me that would make it very unique, it would be self-hosting. Like, is this anything that you dream of at all for a far future where you have a self-hosting Julia?
Well, yeah, of course, every programming language designer always dreams of that, right? But it's another interesting thing that has been an explicit non-priority of ours over the years. Is we have just always said we don't care about that. I mean, it's like, yeah, it's cool, but it usually doesn't really help many users of the language all that much. So, in fact, there's some people make the argument that the obsession with self-hosting has led to a bunch of languages that are mostly good for writing their own compiler.
Yeah, that's true.
But then, actually, Lori Tratt has a great essay about this, about whether maybe self-hosting is overrated. But we are kind of getting there, because the parts are actually getting gradually rewritten. So the front end, which was in Scheme, the parser has been totally rewritten in Julia, and it's a much better parser in many ways. It's way better than the old one. So that's now in Julia, and now the next stage of the compiler, the lowering stage, is well on its way to being implemented in Julia. So that's being done as well by Claire Foster. So that's that whole piece of the compiler is going to be in Julia pretty soon, and then the back end, that part's a little bit tough. Well, we already have a lot of the type inference and optimizations are actually already written in Julia, and they have been for a long time. They always were, I think. So that's already there, and then it's only really just the back end, because we're interfacing to LLVM, which is C++. So it's much more convenient to call it from its native C++. So I'm not sure if we're going to get around to redoing the back end, but maybe someone will eventually. But then we'll have pretty much the whole thing, and I think. But then at that point, you want to have more of a separate compilation story, because you need the compiler to be separately compiled. So,
but
I
also
think want that first.
Yeah, sorry.
Yeah, could you ever JIT compile the compiler itself?
Yeah, I mean, and we do actually. I mean, we can. I mean, we certainly could if we wanted to. The parts of it that are written in Julia, we can. Yeah, we can.
I guess so. Yeah, like I guess different optimizations and such, you can revise them in and such. Yeah.
You can. Yeah, I mean, we don't really. We actually don't want to, because we don't want to waste time recompiling the compiler. So we actually deliberately try to avoid that. But we could.
But so you said this is a non-priority, but how much bigger is the priority list that you need to get done before you can start working on the quote fun stuff?
Well, I mean, I don't know if I would ever consider it the top priority to be, okay, let's get self-hosting. Now that's the top priority. Let's make it self-hosting. I don't think I would ever come to that point. I mean, it just doesn't seem so important to me that I would ever really want to deliberately do that. But I think we might kind of get there gradually. Okay. More and more pieces are going to get rewritten in Julia, and it'll get to the point where eventually someone's going to do the experiment of, okay, you know what? Maybe let's try to make just a simple but functional backend for Julia written in Julia, and just do the simplest thing that could possibly work. And then if you get that working, you can put together a proof of concept, fully self-hosted compiler, and at that point, people will get excited about it, and then they're going to start developing it. And so I think it'll just kind of happen eventually, But I don't think it'll ever be like a major blocker for anything. But it'll be fun if that happens.
Yeah.
So okay, so let's say, you know, like binaries are just completely done, and like, you know, the gods of Julia just hand you down like this piece of code, and suddenly it's just like all your binaries are, you know, all your binaries are compiled as fast as possible and as small as possible, right? What's next on the list? Like, what's your next thing? Or you're just like, okay, this is the big problem we're going to solve.
Oh yeah, so I alluded to this earlier. I think it would be static analysis. So
Okay,
and
yeah.
and by which I mean tooling, because we already do a lot of static analysis, but this would be all kinds of tooling around that. So I want to be able to, you know, I'd like to have an easy to use interface to, you know, check or prove whatever I want to about my program. Like that would be the dream. Like I'd love to be able to point at a piece of code and say, like, you know, prove that this variable is always greater than 0, you know, or something like that, right? And then behind the scenes, we would maybe call an SMT solver or something like that, and you know, make that happen for you. So I'd like to see like that kind of tooling increasingly get developed. And there's all kinds of, you know, this inexhaustible amount of stuff you can do with that. But I think that would be very cool, and I think that's the thing we would do next.
All right. Well, Jeff, is there anything else that you want us to maybe ask you?
I'm pretty satisfied with that. I think that's fine.
Right. Do you want to do the honors, Chris, wrapping up?
Well, I think that was a very good talk. I think we've learned a lot about, you know, Julia, the compiler, and, you know, making our binaries as small as possible. So it's been nice having you, Jeff. It's always nice to see you around in our open source spaces, especially deep within the compiler. Every time we click the enter button to the Julia REPL, you show up on our computer to say hi, right? So it's nice to have you here.
Yeah, thank you for the fun chat.
Thank you, Jeff, and thank all the listeners at home to also tuning in and learning about the Julia compiler and what the future has in store for us. And we're looking forward to hear you again next time.
Yep. Bye, everyone.
See you later.
Bye.